Hello, my name is Konstantin Mikhailov, and today I will be presenting a talk entitled Towards Convergent IoT Connectivity, Vision, Challenges, and Case Studies. First, allow me to introduce myself. I am a tenure-track associate professor specializing in convergent IoT communications within the Center for Wireless Communications, Network and Systems Unit. Over the past 15 plus years, my research has centered on wireless connectivity for the Internet of Things across various sectors, focusing on the design and efficient utilization of future IoT devices, systems, and applications. In today's presentation, I will share my vision on some of the critical aspects of future IoT communication and provide a high-level overview of some of our ongoing activities. But before delving into our discussion, it's a good practice to clarify the terms we will be using. In the case of IoT, this is especially important as there is no universally agreed upon definition. So, what is the Internet of Things? When I pose this question to students and colleagues, the most common response is that IoT refers to things which are connected through the Internet. This leads to two subsequent questions. What are things and what is the Internet? Can a thing be an electronic label, a sensor, a drone, a smart vehicle, or perhaps even an entire smart city? Moreover, does an IoT thing necessarily have to be a physical object? Moving from a thing to the Internet, what is the relationship between the Internet that underpins the Internet of Things and the Internet protocol, which is the foundation of the World Wide Web? Does IoT have to rely on TCP/IP protocol stack? In my work, I adopt the most general interpretation of Internet of Things, treating it as a network of both physical and virtual instances, interconnected without explicit limitation of the technologies and protocols this connectivity is based on. This is how I will be using this term in this presentation also. However, let me emphasize that unless stated otherwise, speaking about connectivity today, I will be referring to connectivity between the physical elements of the Internet of Things. So, why is IoT connectivity important? The IoT is a cornerstone for many existing digital services, and even more so for those anticipated in the future, particularly in relation to cyber-physical systems, digital twins, Industry 4.0, smart cities, and smart grids concepts. Different sources provide various figures, but it is evident that billions of IoT devices are currently operational around us, and their growth rate far exceeds that of other device types. This trend presents a significant market opportunity. Moreover, from a sustainability perspective, the impact of IoT is increasingly apparent. If the most pessimistic scenarios materialize, the carbon footprint of IoT could soon rival that of a country like Japan. Therefore, while IoT in general and connectivity for IoT in particular present great opportunities, it also raises critical challenges that must be addressed. So, what is the greatest challenge related to IoT connectivity? If we were to encapsulate it in a single phrase, IoT connectivity is a perfect case of one size doesn't fit all. There are dozens of different verticals, each with thousands of use cases and applications, and each of them imposes specific communication requirements. So, let's consider several examples. In the context of nature monitoring, or, for example, smart transportation applications, there is a need for energy-efficient periodic communication that is accessible in every region of the globe. Additionally, the ability to localize devices in these applications would be a beneficial feature. Conversely, critical applications in smart healthcare and intelligent transportation services, such as, for instance, autonomous driving, prioritize the reliability and robust delivery of high-priority traffic. Notably, the communication requirements may also vary depending on space, time, and specific context. This leads us to a fundamental question: how can we effectively meet all the diverse requirements of the Internet of Things? In my view, the answer to this question involves four important steps. First, we need highly efficient connectivity technologies capable of addressing diverse requirements, which we must use effectively. As you can see, there are two parts to this. Initially, we need efficient connectivity technologies capable of meeting the needs of diverse applications. However, this alone is insufficient. It is crucial that experts designing these applications are aware of and can identify the most suitable communication technology for each specific use case. Based on my experience with industrial projects, the challenge often lies with the latter. Secondly, for many years, IoT connectivity has primarily relied on relatively static and isolated 2D networks. I believe that in the future we must move away from this comfortable vision towards much more dynamic systems, which will operate in 3D and often integrate multiple, and in long-term perspective all, communication networks and technologies. Another significant trend involves increasing the functionality of the network beyond the simple transfer of a sequence of bits from point A to point B. The integration of sensing, wireless power transfer, and computing with communication offers a promising potential to enhance the functionality, sustainability, and resilience of future IoT networks. Each of these three steps significantly increases the complexity and dynamism of future IoT networks. To manage this, the only way forward is to make the future IoT networks and their components more flexible and intelligent, and artificial intelligence plays a crucial role in this process. Next, I will briefly illustrate how some of these aspects are addressed in my work and that of my group. Addressing the first of the four discussed points, we actively follow and study the evolving landscape of IoT communication technologies, both to understand the capabilities of individual technologies and to explore ways to enhance their efficiency. On the left-hand side of the slide, in blue, are shown the radio access technology we have previously worked with, and in red, those we are actively working with now. The chart on the right presents some illustrative results from our previous studies related to long-range frequency hopping spread spectrum physical layer of the LoRaWAN technology, which is particularly interesting to allow a ground IoT device to send small data packets to a satellite-based gateway. Specifically, the upper chart compares the scalability for a setup closely mimicking the real-life application of autonomous ship monitoring with conventional LoRaWAN, while the lower one demonstrates the energy consumption profile of an LRF-HSS terminal at different phases of its operations. However, what should we do if we find out that a single connectivity technology cannot meet the needs? Do we always need to develop a new technology? Not really. One promising concept that we look at and that can help addressing this issue is multi-connectivity, and particularly multi-radio connectivity, which refers to enabling IoT devices, or more broadly any element of IoT network, to utilize more than one radio access technology, either simultaneously or, in case if our resources are limited, sequentially. The current picture illustrates the different architectural solutions for multi-connectivity at IoT node level, along with their advantages and disadvantages. For instance, the concept of multi-connectivity is explored as one potential solution in the development of a practical data management system with embedded sensors for improved environmental management and transparency of dairy farming, the ERANET SOFANT a T4D project. For this project, we developed a methodology and carried out an analysis of the potential performance expected from conventional cellular networks in dairy farming barns. One of the surprising findings for us was that even in the relatively densely populated Central European regions, the cellular connectivity from inside the farm barns is likely to be poor and may not always enable the provision of reliable service for smart agri-food applications. Therefore, currently, we are examining how this can be addressed based on the hybrid and multi-connected network approach. Another major disruptor for the Internet of Things connectivity landscape, and particularly for areas currently not reliably covered by existing telecom infrastructure, is non-terrestrial networks. As illustrated in the picture on the left, future non-terrestrial networks are foreseen to have multiple layers. Of them, 5 are the most critical. These are, from top to bottom, geostationary, medium, and low Earth orbit satellites, high-altitude platforms, and, closest to the ground, unmanned aerial vehicles. Each of these, depending on the scenario and application, might become an IoT device requiring connectivity service, or serve as an element of IoT connectivity infrastructure. The functionality might also change over time. For instance, if the terrestrial network becomes down for whatever reason, the NTN might have to step forward to replace it. The enablement of communication between the different layers of this structure, and particularly between space and ground, introduces many exciting challenges due to the high mobility and dynamism, great communication distances, and limited resources. Another substantial challenge is the integration between terrestrial and non-terrestrial networks to allow devices to effectively communicate in and roam between the networks. Identifying the importance of looking at NTN and their integration with terrestrial networks from the perspective of IoT, together with my colleagues, Professor Hille Alves and Marco Höchtö, we edited a book on the topic, which includes contribution from renowned experts in the field. So, if you are interested in learning more, the book is already out and is available from Wiley and IEEE Xplore. Currently, we are engaged in two exciting projects dealing with non-terrestrial IoT connectivity. The first, funded by Business Finland, and involves collaboration with VTT Technical Research Center of Finland and many great industrial partners. This project focuses on investigating the potential and developing a wireless connectivity solution based on 5G reduced capability radio access technology, operating effectively over non-terrestrial satellite infrastructure. RedCap presents the first true 5G IoT connectivity technology, and it is aimed at enabling lower cost, lower complexity, longer battery lifetime, and smaller form factor than regular new radio devices, which makes it particularly suitable for advanced IoT applications. The initial results of our analysis, which are currently in press, show that RedCap features great potential not just for terrestrial networks, but also for non-terrestrial. Another activity started quite recently is the second phase of the 5G Emerge project by the European Space Agency. The project develops integrated satellite and terrestrial system based on open standards to enable high-quality content distribution services. Telecommunications satellite will be used to effectively deliver high-demand content, including streaming of live events, as close as possible to the end user, to the neighboring base station, or even directly in users' homes and vehicles. In this project, we contribute to the task focusing on physical and link layer simulation and modeling of non-terrestrial links. Finally, a good illustration of activities approaching the remaining two of the 4 points is the work we carry in the Smart Networks and Services Joint Undertaking Super IoT project. The unique concept of the project, based on the use of dual-mode optical and radio connectivity, energy harvesting, and positioning, has already been presented by the principal investigator of the project, Professor Markus Katz, as a part of the 6G Talk series. Therefore, I will not discuss it in details. The focus of our team in this project is related to Work Package 3 and involves the design and proof-of-concept implementation of the network architecture accommodating this unique optical radio duality and integration of beyond communication functionalities. Also, we develop multiple attribute optimization solutions for access point assignment and handover. With this, let me conclude my talk. If you would like to hear more about our research or discuss potential collaboration, please feel free to contact me.